Everyone, and welcome to my YouTube channel, Enthalpy Chemistry. If you've not yet subscribed to my YouTube channel, please go ahead and subscribe and turn on the notification button so each time I upload a video, you'll be the first to know. So today we shall be learning how to calculate enthalpy change using bond enthalpy. Now, before we continue, it's good we understand what enthalpy is, enthalpy change, and bond energy. So let's take a look at this. So enthalpy, denoted as uppercase H, is the thermal energy contents of a system, while enthalpy change, denoted delta H, remember the small triangle means delta. So enthalpy change delta H is the transfer of thermal energy during a chemical reaction. Now it should be noted that this thermal energy can be transferred from the surrounding to the reaction mixture or from the reaction mixture to the surrounding. So let's note the following concerning enthalpy change. The first point we want to look at is this. When heat is released from the system to the surrounding, that is in the case of an exothermic reaction, enthalpy of the system decreases and delta H is negative. So let's take note of this. When delta H is negative, the reaction is described as an exothermic reaction, and in such case, heat is released to the surrounding. That is, heat is released from the system to the surrounding. The second thing we want to take note of is this. When heat is taken in by the system from the surrounding in an endothermic reaction, the enthalpy of the system increases and delta H is positive. So when delta H is negative, when it gives us a negative value, let's say we calculate delta H and it gives us a value of, let's say, negative 39 kilojoule per mole, it means here we are talking about an exothermic reaction. On the other hand, if we calculate the value for delta H and it gives us a positive value, let's say plus 51 kilojoule per mole, in this case, it means the reaction is an endothermic reaction. Okay, now that we know about that, let's move to the next stuff. So it's also good we understand what bond energy is. And bond energy is simply the energy required to break a particular type of covalent bond. Let's say we have a hydrogen molecule that is made up of two hydrogen atoms linked by a covalent bond. If we want to break this bond to release separate atoms, hydrogen atom plus a hydrogen atom, in this case the energy we use to break this bond is what we call bond energy, and it has a certain value for each specific type of bonds. We are going to look at that when we solve some examples. Now the next thing we should also take note of here is that in a chemical reaction, energy is absorbed to break bonds. This is very important for you to note. So energy is absorbed whenever we break bonds, and in this case we talk of an endothermic process because we are taking in energy. So energy is absorbed to break bonds, and bonds are always broken where? In reactants. Very important to note this. Bonds are broken in reactants, and energy is also released when new bonds are made. That is, it is an exothermic process. Remember, the absorbing of energy is endothermic, while the release of energy is exothermic. And new bonds are made in products. Very important for you to note this. New bonds are made in products. Now that we have all this information, how can we calculate enthalpy change of a reaction? So, to calculate the enthalpy change of a reaction, we first of all have to calculate the total energy required to break bonds. Remember, bonds are broken in reactants, minus the total energy that is given off when bonds are made. And remember, bonds are always made in products. So total energy for bond breaking, and remember this occurs in reactants, minus the total energy for bond making, and this occurs in products. So it is very important to remember this formula because it's going to help us a lot. Now that we know about this, let us take a look at an example. Okay, so here we have an example for us to try. Let's see, nitrogen reacts with hydrogen to produce ammonia. The reaction is exothermic. Here we've been given some information. The reaction is exothermic. Now, what can we deduce already from this? If the reaction is exothermic, it definitely means that when we calculate our delta H, which is the energy change for the reaction, we should have a negative value. That is what it means. So if you were to calculate your energy change for a reaction and you get a positive value, hey, you've probably made a mistake and you need to correct that or recheck your work. Now, so the bond energies are shown in the table. You can see we have the bond energies here. What does this information mean? So we have, for example, a nitrogen molecule. A nitrogen molecule is made up of two nitrogen atoms like we have here, and they are linked by triple covalent bonds. So if we want to break this bond to produce, if we want to break that bond to produce separate nitrogen atoms, we need a certain amount of energy, and that energy has been given here in the table. Similarly, if we want to break a hydrogen-hydrogen bond to, of course, release hydrogen atoms, we need a certain amount of energy, 436 kilojoule per mole. So the same applies for a nitrogen-hydrogen bond. So how can we then use this information to calculate the energy change of the reaction? Remember, the question wants us to calculate the energy change of the reaction. So let's see how we do that. Okay, here we go. So remember the formula we just saw a while ago. Enthalpy change is the total energy of bond breaking minus the total energy of bond making. So let's start by calculating the energy for bond breaking. And remember, bonds are broken in reactants. So here we go. We start. We need to calculate bond breaking. Now, over here, this equation can be represented using, this equation can better be represented by drawing the actual structure of the molecules. So we have over here, that is it, the nitrogen molecule, plus we have 3 hydrogen molecules. And what does that give us? It gives us, here we have 2 molecules of ammonia. Now this is the structure of ammonia. If you don't know how to do this, revisit your lesson on bonding and structure of molecules. Okay, so that is the equation. Now let us see. Remember, for the reactants here, we have nitrogen and hydrogen. Those are the reactants. So in these reactants, we are breaking the nitrogen-nitrogen bond, and we are breaking the hydrogen-hydrogen bond. So let's see. Over here we have nitrogen, so we are breaking the nitrogen-nitrogen bond, plus we are also breaking the hydrogen-hydrogen bond. But remember, there are 3 molecules of hydrogen. So it means that we're going to multiply the value by 3. So here we have, let's first of all represent it this way. It will be better. So we have 3 times the hydrogen-hydrogen bond. Now let's insert the values. So for the nitrogen-nitrogen bond, we have 945 plus 3 times 436. Okay, so if we perform the math here, what do we have? We're going to have 2253 kilojoule per mole. Now, mind you, this is not the final answer. This is just the energy required to break bonds. Now, we need to calculate as well the energy given out when bonds are made in products. So let's do the second part. Now, over here we have bond making. Bonds are made in products. And the product here is the ammonia molecule. I'm talking about this. This is the product. So that is the product, the ammonia molecule. Okay. Now, in this product, let's see how many nitrogen-hydrogen bonds we have. So this nitrogen-hydrogen bond, that is 1, this is 2, and this is 3. So we have 3 nitrogen-hydrogen bonds in 1 molecule of ammonia. but over here we have 2. So it means in total we're going to have 6 nitrogen-hydrogen bonds. If that's difficult for you to see, you could still represent this molecule like this. Remember, we have 2 molecules. So let's represent the first one. That is it. This is the first nitrogen-hydrogen molecule. This is the second. Okay. Now, let's count the number of bonds that have been made. 1, 2, 3, 4, 5, 6. So you see, we have 6. In this case, therefore, we're going to have 6 multiplied by the NH bond. Remember, whether you represent it as an HN bond, it is still the same as an NH bond. Okay, so let's insert the values and see what we get in this case. Here we have 6 multiplied by 390 from the table. That is the value. We have it there, 390, and that gives us 2340 kilojoule per mole. Now, we go back to our formula. Our formula states that we should take the total energy for bond breaking minus the total energy for bond making. So we have our total energy for bond breaking and bond making. This therefore means that the energy change, delta H of the reaction, will be 2253 minus 2340, and if you punch that, you're gonna have negative 87 kilojoule per mole. So let's look at the different options we have here. So you will see that B is the correct answer, and that ties with the information we're given in the question. Remember, we're told that the reaction was exothermic, and our enthalpy change is also negative, confirming that the reaction is truly exothermic. So now that we've solved an example, I would want you to try these exercises. Actually, we've got 3 of them. So let's begin from here. This is the first exercise. So go ahead. Let's look at the second exercise. This is the second exercise. Good. Those are the answers we need to select from. And this is the third exercise. So please go ahead, pause the video and try to solve these 3 exercises. And later on, come back to the video and see if you got the answers right. I believe you've tried the exercises, so let's now correct them together and see if your answers are correct. Okay, so let's start with the first. Hydrogen peroxide, we've been given the structural formula of hydrogen peroxide, decomposes to form water and oxygen. This is the equation for the reaction. The bond energies are shown in the table. The reaction is exothermic. Oh, here again, we've been given a clue. The reaction is exothermic. So this means our delta H has to give us a negative value. Okay, what is the energy change for the reaction? Now, remember what we always do. So we have to start by calculating bond breaking. So let's look at bond breaking. And remember, bonds are broken in reactants. Now, to better understand this, let us draw the spread out structure of the molecules we have here. So we have hydrogen peroxide. We've been given the structural formula. So we have this. Okay. And we obtain the equation. The decomposition equation gives us 2 water molecules. So here we have water. Okay, plus an oxygen molecule. That is an oxygen molecule. So in the reactants, let us see what we have. Remember, in the reactants, we have to break. This is 1 HO bond and 1 HO bond. But there are 2 molecules. So we need to multiply that value by 2. So in effect, we have 4 HO bonds. So this is what we're going to write here. We have 4 OH or HO bonds. Now, if you still are not seeing it, we have 2 molecules here. This one has been represented. Let us represent the second. Okay, so now you can clearly see we have 1, 2, 3, and 4. So you can clearly see the 4 OH bonds. So we have 4 OH bonds plus, what do we have again? Here we have to break one oxygen bond. I'm talking about this. We also need to break this bond. And remember, there is a 2 here, so we multiply by 2. 1 is here, 1 is here. So in effect, we have plus 2 OO bonds. So we have plus 2 OO bonds. What does that give us? Let's insert the values. So here we have 460 plus, over here we have 2 times 150. So if we perform the math correctly, we're going to have 1990 kilojoule per mole. So that is it for bond breaking. Let's now move over to bond making. So here we have bond making, and remember, bonds are made in products. So let's see. Here we have 2 water molecules. So here we have one HO bond, one HO bond. If we multiply by these 2, we have 4 HO bonds. If you're not seeing it, let's represent the second water molecule. This will be the second water molecule. So you can clearly see the 4 OH bonds over there. So here we have 4 multiply the OH bond plus we have one oxygen bond. So let's go ahead and insert the value. So we have 4 times 460 plus 496. Of course, the values are gotten from the table over here. Don't be confused, guys. Okay, now if we perform this operation, we're going to have 2336 kilojoule per mole. Okay, now we come to our formula. Remember the formula we have: enthalpy change of reaction delta H is equal to the total energy for bond breaking minus the total energy for bond making. So here we simply have to insert the values we've calculated here. So our delta H, therefore, which is the enthalpy of reaction in this case, we have 1990 minus 2336. And what does that give us? It gives us negative 346 kilojoule per mole. Do we have this answer amongst the options? Negative 346. Of course we do. So here we have A. So A is the correct answer. Did you get that right? Okay, let's move to the next question. Yeah, this has got to do with an organic compound. So let's see. Ethene burns in oxygen to form carbon dioxide and water vapor. Here we've been given the structure of the molecule, so it makes it even much easier. The bond energies are shown in the table. What are we supposed to do? What is the energy change for the reaction? Okay, so let's see how to solve this. Like we know already, we begin with bond. So let's start with bond breaking, and this occurs in reactants. So let's see. Here, what are we breaking? We are breaking one CH bond, one CH bond, one CH bond, one CH bond. So in effect, we are breaking 4 CH bonds. Okay, plus let's also see, remember, we are breaking one carbon-carbon double bond. We are also breaking this bond. So we have plus the carbon double bond. What else do we have? Okay, now we also have to break these oxygen bonds, and there are 3 molecules. So in effect, we have this thrice. So we are breaking 1, 2, 3. Okay, now what do we have? So we have plus 3 oxygen bond. Now let's insert the values. So we have 4 times 410. Of course, we are getting the values from the table we've been given. plus for the carbon-carbon double bond is 610 plus 3 multiplied by 497. So if we perform that math, what do we have? We're going to have 3,741 kilojoule per mole. So that is it for bond breaking. Let's now move over to bond making. And like we know, this occurs in the products. So let's now tackle bond making. Okay. In the products. So let's see what we are doing here for the bond making. So here we are making actually one oxygen carbon bond, one oxygen. So we have two, but remember there is a two here. We have two molecules. So in effect, we have this twice. So here we have 1, 2, 3, and 4. So over here we have 4 times the carbon oxygen bond. Remember, whether you represent it as such, OC or CO is still the same, right? Okay. Plus, what else do we have? Okay, we have a water molecule. We have 2 water molecules. And remember, in one water molecule, we have 2 OH bonds. So in 2 water molecules, we're going to have 4, like we saw in the previous case. So here we have 4 times OH bond. So substituting the values, what do we have? We have 4 times 805 plus 4 times 4, 60. If we perform that math, we're going to have 5060 kilojoule per mole. Okay, now we have our values for bond breaking and we have our values for bond making. Now, applying our formula, we have this. So our delta H for the reaction, it's equal to 3,741 minus 5060, and that's going to give us negative 1319 kilojoule per mole. Do we have the option here? Of course, option C. So did you get this right? Okay, now we move to the last exercise. Let's see. The equation for the combustion of methane is shown. We have the equation here. The energy change for the combustion of methane is this. So in this case, we've rather been given the value for delta H. So delta H is equal to negative 890 kilojoule per mole. Okay, that's good. Now, what do they want us to do? The bond energies are shown in the table. Yes. What is the bond energy for the CO bond? So in this case, we need to calculate the bond energy for the CO bond. Anyway, don't worry about that. It's pretty easy. Let's do it together. Okay, remember our formula already. So we're going to make use of that formula to be able to calculate the value for the CO bond. So here we go. Let's begin with bond breaking. So bonds are broken in reactants. To make it easier, let me give you the spread out structure of methane. So this is methane, the CH4. So in one molecule of methane, we're breaking 1, 2, 3, 4. So we are breaking 4 CH bonds. So we have 4 CH plus over here we have 2 oxygen bonds. Okay, so we have 2 oxygen bonds, double bond of course, like we saw in the previous case above. Okay, so what does that give us? Let's substitute the values here. We have 4, the CH we have 410 plus 2 we have 496. So what does this give us? It gives us 2632 kilojoule per mole. So this is the value for bond breaking. Now let's move over to bond making. So for bond making we have, let's see, bond making. Remember the products we have here, carbon dioxide and water, and earlier on we saw the structure of carbon dioxide, that's it, and water, we saw this. Remember we have two molecules here. So in effect, in the products we are making 1, 2. So we are making 2 CO bond plus, now remember there is a 2 here. So in effect, we have 1, 2 multiplied by 2, it gives us 4. So we have 4 OH bond, or if you like, you call it HO bond. So let's substitute the values. What do we have here now? We have 2 multiplied by the CO bond. But this is what we are looking for. We don't know the value. Plus 4 times OH bond. We know the value for OH bond. That is 460. So what do we have? Now we're going to have 2 CO plus 1840. Here we have kilojoule per mole. Remember, this is what we are looking for, the bond energy for the CO bond. Now, coming back to our formula, enthalpy change of reaction is equal to total energy for bond breaking minus total energy for bond making. We're going to use that formula to help us. Were we given the value for the enthalpy change? Yes, in the question we're given the value. So that is it. Now, let's see how we're going to do it. So in this case, our delta H has been given. We have it here, negative 890 kilojoule per mole. So we can simply just go ahead. I think it's even better that way. So since we have our value already, we're going to have negative 890. It will be equal to bond, the value for bond breaking. Remember, this is the value for bond breaking. 2632 minus bond making. And for bond making, we have this plus 1840. Okay, so that's what we have. Now let's open the brackets. We're going to have 2632 minus 2 CO minus 1840. Okay, negative 890. So we continue down. What do we have in this case? We're going to have negative. Let me take off this. Okay, so here what we have is this negative 890 will be equal to, if we take this minus this, we're going to have 792. So 792 minus 2CO bond. Okay, I think it's getting more interesting. So here now we're going to have 2 CO bond. It will be equal to, what have we done? So this is what we've done. I take this man over here and I bring this over here. Remember, when the negative sign crosses the equality sign, it changes. So in this case, we're now going to have 792 plus 890. Great. So here now 2 CO bond will be equal to 1682. Okay, now the CO bond, we divide both sides by 2. So it is going to give us plus 841 kilojoule per mole. Okay, now do we have this answer amongst the option? Plus 841 kilo, of course we do, B. So that's it. So you see how easy it is to calculate enthalpy of reaction using bond energy values. And even before that, let's take a look at the example we solved earlier on. Remember this example? Okay, let's look at something else. Now, in this example, remember when we calculated the energy change for a reaction, the value was negative 87 kilojoule per mole. And the reaction, this was the reaction, nitrogen plus hydrogen to give us ammonia. Now, let's see. The reaction can be reversed, of course. And when the reaction is reversed, we have this. What would be the enthalpy change for the reaction? So if we reverse that equation, what would be the enthalpy change? It is simple. Now, we had this value when we used the equation in this form. So if we reverse that equation, simply we come and reverse the sign here. So it's going to be plus 87 kilojoule per mole. Chemistry is simple, right? Okay, so thank you so much for following this video. Remember, please, if you've not yet subscribed to my YouTube channel, go ahead and subscribe, turn on the notification button, comment on the video, like, and share the video. So thank you so much. Until next time, have a safe day and see you soonest. Bye-bye from this end.